polynomial zeros, equidistribution of polynomial zeros. So in many cases, I showed pictures last time, the roots of a polynomial tend to lie uniformly almost uniformly distributed on the unit circle. They're neither exactly on the unit circle nor exactly uniformly distributed in angle, but close to. That's what pictures show. And towards that, we began proving one important theorem. First, we separated it into two parts. One is the radial distribution and angular distribution. Radial distribution means we want to say all the, say, zeta 1 up to zeta n are the roots of P. Under some conditions, obviously it's not true for all polynomials. Under some conditions, zeta 1, the mod zeta j's are pretty close to 1. So that is the thing to figure out in radial distribution. I said this is easy and we will do it at the end. The key part is angular distribution, which is you'll take not mod zeta j's, but zeta j or mod zeta j. These are the projections of the zeros onto the unit circle. And we look at probability distribution, which puts mass 1 over n at each of them. That is, we count, in other words, this number, this is the proportion of roots that lie in a given sector given by an arc on the circle. If you give an arc on the circle, that defines a sector in the complex plane. So what proportion of roots are in that sector, that is measured here. We should compare it to the angle of that sector, meaning angle by 2 pi, the length of the arc by 2 pi. We want to say this is small, and there Euler's theorem was the theorem which said that in terms of some quantity which measures the size of the polynomial on the unit circle. Okay, so P is a polynomial. We assume that A0 and An are not zero, the first and last coefficient. And then we showed that the angles, if you look at the angles, the proportion of roots in a sector minus the angle of the sector over 2 pi, that is bounded by a constant times square root h of p over square root of n. Square root n is the degree of the polynomial. H of p is the size of the polynomial on the unit circle measured like this. It is the log plus mod p over square root a0 an integrated over the circle. If you assume for simplicity a0 and an are 1, okay, so then it's basically you take the polynomial log plus of the polynomial. That is, you don't care if somewhere it is 0, then log plus means positive part of log. You average it on the unit circle. That is a measure. It's a bit complicated looking, but as we said, it can be bounded by some easier to control quantities. Instead of doing an integral, you can just bound it by the maximum. Since it's an average, you can bound it by the maximum, which becomes log of the subnorm of the polynomial on the unit circle divided by a0 an, square root of a0 an, which can further be bounded by, since on the unit circle, p of p to the I theta can be bounded by sum of the absolute values of coefficients, something like this. So because of this, if the coefficients are all not exponentially large, sub-exponential in some sense, then I did something here. As long then you can get that angles are angularly we have equidistribution. Okay. So I was going through the proof of that. So I don't want to go over the entire proof. There was the following point. So one is that first case, we assume that the roots are on the unit circle. So P of Z is an times product Z minus zeta J, where zeta J are on the unit circle. In such a case, so then this we are looking at this one. So this is a measure on the unit circle. This is M. So we use the Euler's theorem bound. So the question was to compute coefficients, Fourier coefficients of this empirical distribution of roots. And for that, it is basically calculating the moments of the roots. That is, zeta j to the power k summed over j equals 1 to n. We have to control. And that is where this claim came in. Okay, which is, I think, something that I have not yet proved. So this claim is something that yet needs to be proved. Okay, we expressed the mu hat in terms of Fourier coefficient in terms of the polynomial, and you kind of see that from there we can get a control, and we got the control that this mu hat k over k is bounded by the h of p basically. Okay, so rather I did it for the log norm p over square root a0 an, and then we get the whole bound. And how to improve that to h of p instead of the, you can leave it at the integral level. Then you have to do a little more work, and you will get h of p. Okay, so this much we did, but this is only when the roots are on the unit circle. So one thing to prove is this claim, why mu hat of k is given like this. And the second is, what if roots are not on the unit circle? I went over it just in case it was quick. Let me just tell it. So the idea is of Shu is that you take any polynomial with roots anywhere in the complex plane. We are assuming they are not zero. Okay, so we are assuming zeta j's are not zero. That's why otherwise the last coefficient would have been zero. So if the roots are not none of them is zero, then you can project them to the unit circle. Problem with the zero roots is that it has no angle, right? You can't talk about its angle. So, but non-zero roots, you can project them to the unit circle. So we get a new polynomial whose roots are the angular projections of the roots of P. Then, of course, the angular distribution of Q and P are same. And for Q, we know a good bound, mu k of I minus m of I, we have a bound for that. So in terms of, so we know that, yeah, what we know is that, what I mean is here, mu q of I minus m of I, we know a bound of the form constant square root h of q over square root n is the degree. But this is same as mu p of I of minus m of I. So all I need to show is, this is the thing to show, that this is bounded by h of p. If you can show that h of q is bounded by h of p, then you're done. That is, now once you set yourself the task to prove h of q less than h of p, okay, so you want to prove h of q less than h of p, that is easily implied if q is less than p on the unit circle. Well, not exactly p, but because there is an a naught by an. Okay, so this q has yeah, anyway, so this is h of q will have q over n. Yeah, oh sorry, I made a mistake. So q, the coefficients, the a naught coefficient of q is same as an actually. See, the leading coefficient is an z to the n. What is the constant coefficient is an times the product of the roots with minus 1 to the n. So absolute value of that is also an. So when I do the h of q for p, it is mod p over square root a naught an. That is what we take, and then take the log plus and integral. For q is a naught is same as an, so it is mod an. So which comes to showing that q is bounded by p over square root mod a naught by an on the unit circle. Now you write everything in terms of the roots. Okay, q is the product of an times e to the q of e to the I alpha is product e to the I alpha minus e to the I theta j. So put absolute values, and p is an, put absolute values, mod an e to the I alpha minus rj e to the I theta j divided by a naught by an is the product of the roots. So that is square root of mod rj. So that comes to an inequality like this. So you bound the jth term by jth term. Yeah, an cancels. You just bound jth term by jth term. That is e to the I alpha minus e to the I theta. You bound by e to the I alpha minus r e to the I theta divided by square root r. This is a simple exercise. You just square it and check. Okay. So that's how you reduce this Shu trick reduces the question from general polynomials to polynomials lying with zeros on the unit circle. Any questions so far on this? No? Okay. So then what I want to now do is prove the claim, and then we will go to the radial distribution. So where does the claim come from? Okay, so proof of the claim remains. So mu hat of k, what is it that we have to show? Mu hat of k is this one. So mu hat of k, remember, is this 1 over n this. So let's cancel the 1 over n. So basically what I want to show is summation e to the minus k. So let's just do it with k. Okay, so what we need to show is what did I call them? Theta j, right? Theta j. Is equal to, let me see what was there, 2 mod k times this one. Okay, 2 mod k log. Okay, mod p divided by an. For p with roots on the unit circle. So this was in the case where the roots are on the unit circle, right? E to the I theta 1 up to. Okay. So this anyway, so how do we show something like this? So the point to realize is, okay, so let's see what, let's reduce what we have to write in terms of this. So this is, this thing is actually 2 mod k. This is for k not equal to 0. For k not equal to 0, I think. Anyway, so.
Sir, is there a minus sign, like e to the minus I k theta j?
Yeah, I removed the minus on both sides actually. Mu hat of k has e to the minus I k theta j, and this also had a minus k, so I just removed the k. I prove it for all integers k except 0.
Okay, thank you.
Okay, so I just avoided that. Okay, for k not equal to 0. Yeah, so there it was with minus k both sides. Yeah. So this one, you see, what does this mean? P of z is actually product z minus e to the I theta j equals 1 up to n. So what is this log mod times an? Of course, an is there. So log mod p of e to the I theta over an is actually 0 to 2 pi. We get a sum because it's a log. And the an cancels. What we are left with is e to the I theta minus e to the I theta j. Okay, so that is what is here. And then I have e to the I k theta d theta over 2 pi, which is, of course, the sum. Okay. So this is, so to prove this, what do? I do term by term. So this is implied if there is a sum of j things, sum of j things. I'll show jth term here equal to jth term here. So it is implied by showing that just e to the ik, let's call theta j as some alpha. E to the ik alpha is equal to 2 mod k is 0 to 2 pi log mod e to the I theta minus e to the I alpha times e to the ik theta d theta over 2 pi. Okay, I just need to show this integral. This is a very specific integral. You can imagine doing it by hand. I mean, it can be done by hand. That's what we are going to do. You can do it with less tricks or more tricks, whatever it is. So see, e to the I mod e to the I theta minus e to the I alpha, you basically get in terms of sine of theta minus alpha or something like that. So in principle, everything here is doable. But with some tricks, it becomes a little less difficult. So what we will do is, so to prove this, proof of this identity, what we will do is, it is a bit easier for me if I just introduce first fix some r less than 1 and consider log mod e to the I theta minus r e to the I alpha. Okay, which is same as if I pull out the e to the I theta, which has absolute value 1 minus r e to the I alpha minus theta. See, this is what is this actually? Log mod. So if you realize, so what is log mod something? So if you have so let's say if z is, let me just say a word about complex logarithm here. Complex logarithm can be tricky. Okay, so one is here. So log, if z is I to the I theta, you would like to say log z is log r plus I theta. But there is no guarantee what is theta. I mean, so theta, there are many possible thetas, so we have to choose one. So in general, that is a complicated thing. I mean, in general, that is an ambiguous thing. But when you are in a neighborhood of 1, so let's say if we are here, so if z is here, then I can choose theta always between minus pi by 2 to pi by 2. I mean, I didn't have to take this disk anywhere in this right half plane, for example. I can define log of complex number as log r plus log I theta, where theta is actually the angle which you have chosen to be between minus pi by 2 to 2 pi by 2. We can always add 2 pi's to that, but I will choose the argument which is, because that makes a difference here. If you choose it to between something plus 2 pi, this will also go up by that much. Anyway, the complex logarithm is just a device that will be helpful here, because then I can write log r as the real part of log z. Okay. And so this is, I will write it as real part of log of 1 minus r e to the I theta minus r. Whatever I do here, if you don't like it, you do it your own way, whichever way. Okay, so I can write it as real part of the complex logarithm, but this in a neighborhood of 1, it has a power series expansion, namely minus summation j equals 1 through infinity. Log 1 minus x is r to the j e to the I j into alpha minus theta divided by j, right? And then I have to take the real part. So which is, yeah, whatever it is, it doesn't matter. So the integral, so therefore the integral, if I integrate 0 to 2 pi log mod e to the I theta minus r e to the I alpha against e to the I k theta d theta over 2 pi. So this is just the same as what I have here, except that I have put an r in front of e to the I alpha. I will let the r converge to 1 in the end. So this is going to be, so this is itself the Fourier expansion, right? I mean, so this is, what is this actually? This is, okay, one more line here. This we can write as sum over j not equal to 0, r to the j e to the ij into alpha minus theta over 2j. Because here I have done j not equal to 0, and so j and minus j together converge to give 2 times the real part of this, right? So e to the ijx and e to the minus ijx together will give 2 times the real part. So I put a factor of 2 here and so on. So this has a Fourier expansion like this. I mean, this is an expansion like this. So from this, you see, if you look at it as a function of theta, what is the Fourier coefficient corresponding to k or minus k, whatever it is there. This is nothing but the corresponding thing here, r to the k. Okay, something is a little strange. Is it r to the k e to the minus ik alpha? Ik alpha over 2k. Actually, sorry, here I should have put mod j. It is not j, but 2 mod j, so that when I add the j and minus j, I get this, and there is an overall negative here. So maybe there is a, yeah, what is it? If I integrate against e to the ik theta, here the j equal to k term alone comes. So there is an overall negative, it looks like. Is that right? Okay, there seems to be a negative. Maybe it is there, maybe it's not there. more or less we have the answer here. Now let R go to, so 2 mod k. You understand how I got from here to here, right? So you just integrate this against e to the I k theta. The only thing that survives is j equal to k term, because that e to the minus ij theta has to be integrated against e to the I k theta. This is the Fourier expansion of this function as a function of theta. So you just get the kth term here, r to the k e to the I k alpha over 2 mod k. And therefore, so now let r go to 1 to get this thing. Okay, I have messed up on the sign somewhere. I don't know what happened. There is a minus. Should there have been a minus here or plus?
No, there is no minus in that second thing. Log 1 minus z. Oh, wait 1 second. Yeah, there is a minus.
There is a minus. Was there a minus in the original? Maybe there is a minus here. Okay. For all I know, maybe there is a minus on this, which is okay as long as I take absolute value here. So it is plus minus. Let me just put it is plus or minus. Okay. Because I only used it with absolute value so that even if there was a minus, it would go away. Let me just check it actually. Where is my notes? What did I do in my notes? Yeah, there I have also forgotten the minus actually, it looks like. Okay, so there should probably be a minus. Okay, let's not worry too much about it. You fix it. So when r goes to 1, you have to argue that this integral will converge to that, and this will of course converge to e to the I k alpha over 2 mod k. Okay, so that's it. Is this okay? So that okay. So now what? I mean, so now you submit and you get back the claim. That's all. Is there any question? Okay, that proves the angular equidistribution. So it's a remarkable theorem. Did I go over the example of z minus 1 to the n? So there, okay. So it is not always equidistributed, but based on the magnitude of p on the unit circle, you can say the roots are angular distribution of roots is like you almost equidistributed. That's an amazing theorem. Okay, what about the radial part? This is actually a bit easier. So the claim is this. So here is the statement of the theorem. Meaning it's not having roots on the circle or anything. It is a polynomial with a naught an not equal to 0. Okay. So none of the roots is 0. So that's one reason why a naught should be not 0. If roots are 0, you can't talk about the angle. That's the problem. So anyway, with roots zeta j, which is rj e to the I theta j, 1 less than equal to j less than equal to n, repeated with multiplicity if needed. So let's give a radial distribution. Okay, first of all, there is a, yeah, let nu p, okay, let's introduce that. Let nu p be the radial distribution, which is puts one mass 1 over n at the radii, delta rj. So this is a measure on 0 infinity. It's a measure, probability measure on 0 infinity. Okay, so the proposition is the following. The claim is, first of all, if you take log of Rj or 1 over Rj, whichever is larger. Meaning if Rj is less than 1, you take log 1 over Rj. If Rj is bigger than 1, take log Rj. So that you get a positive number. Okay. So it's the same as mod of log Rj. I mean, that is, yeah, is that correct? Yeah, it's same as mod log Rj. If I add that, that is bounded by 2 times the same quantity which we use to control h of p. You remember h of p is, I'll just write down, it is 2 times 0 to 2 pi log plus mod p of e to the I theta over square root a naught an and then d theta over 2 pi. That's what this thing is. So it's the same quantity which controls. How does it control? So from this, we can say that actually it's a simple Chebyshev-like bound. If I take 0 to r union 1 by r to infinity. So what I'm doing is, so for r less than 1, so I take, so here is the unit circle. Okay, let's say this is the unit circle and this is the circle of radius r and this is the circle of radius 1 by r. Now what is nu p of 0r? It is the proportion of roots which lies inside here. What is nu p of 1 by r to infinity? It's the proportion of roots that lie outside this bigger circle. So this should be small. If you want to say all roots are close to 1 in absolute value, this we want to say is small. This is the proportion, right? So this will be smaller than, I think, just 2 over n h of p. Let me just see. Is that what I want to say? Yeah, oh, sorry. 2 over n h of p. Sorry, that also depends on, yeah, I mean, it can't be that. It has to depend on r. So it is 2 h of p n log 1 by r. Okay. So this is the radial distribution theorem. Okay, so as a corollary, maybe one it is easier to interpret if you have a sequence of polynomials. So as a corollary, suppose p of z, pn is a sequence of polynomials. Like the above, as above, with coefficients between 1 over bn and bn in absolute value. Assume that the coefficients are between 1 over bn and bn. Bn is a number greater than or equal to 1. 1 over bn is small. Okay, so assume bn is not going too fast. Like before, it is e to the little o of n. Okay, it's not going exponentially. Anything, even it could go as fast as e to the square root of n. That's okay. E to the n to the 0.99 is okay, but it should not be e to the constant n. Then nu pn of 1 minus delta 1 plus delta goes to 1 for all delta positive. Okay. What it is saying is that for this sequence of polynomials, with the proportion of roots that are within 1 minus delta 1 plus delta goes to 1 for any delta positive. This is, if you want, if you know probability language, this is convergence in probability to the delta measure at 1. That's what this is saying. It immediately follows from here, because 1 minus delta 1 plus delta, just take this r. I mean, you don't have to write it in 1 minus delta 1 plus delta form. Take any r less than 1. Look at what happens nu pn of this. Now h of p you have to show by, because of this bound on bn, h of p, there is a log inside h of p. So this will be little of n, but we are dividing by n. So that will go to 0. Okay, I will leave that as exercise. I will leave that as exercise. I mean, just very simple checking. You just have to show that this thing goes to 0. For any fixed r, this goes to 0. That's all you need to show. So this is the radial distribution theorem. Where does it come from? Now, this is actually, I said it is easier, but if you don't know this, then there is something nice to learn here, because it is a good opportunity to introduce one thing called Jensen's formula, which is if you may have seen it in a complex analysis class, or you may not have. So if you haven't seen, I pretty much prove for you now. Okay, but any questions here so far? So if you combine this with that, you get both the radius is close to 1 and the angles are equidistributed. That's what you get.
So Manju, so if we combine both, then you get something in Levy distance, that is a randomly picked root is close to the uniform distribution on the circle.
Sort of. I mean, so Levy distribution in the plane, I don't know, because
Levy distance, I mean.
Oh, sorry, Levy distance. Yeah, sorry. Levy distance. Yeah, probably yes.
So are there like similar results for other like distance stronger metrics? Like
that's what. And the angular part, we have a stronger metric. You mean like this, right? So the angular part is in a stronger metric. We are showing, in fact, this.
Yeah.
So the radial part is, I don't know for what class of. I mean, of course, if you take things like, I suppose you can prove it for sectorial intervals, meaning interval cos.
I see.
Probably, if you combine these two, you can probably prove for such sets.
Right.
That the measures are close enough, meaning it depends on the Bn really. It's basically Bn by n is what controls this. If Bn is polynomial, then it's like log n by n type. Square root log n by n. Here there is no square root. In the other one there is a square root.
Yeah.
That is the smaller one. So I think you will get that, but I haven't. I haven't seen it written out somewhere like that. Usually separate out these two things.
Right. Okay.
Did you have other distance in mind, or this kind of one, like the?
Yes, like the DBL rounded Lipschitz. Those are hard, probably. Yeah.
That somehow, I don't know. Here we wanted to reduce it to intervals, but this type of trick may be easier to convert to linear statistics also.
Yeah.
Angular distribution. If you assume Lipschitz, you may get an even better one. But I have not seen that actually.
Okay.
It's a good question. So let me explain to others what Somendu is suggesting. So this is one way of measuring how close mu is to m. But there are other ways. A very common one, use this. So one way to measure how close mu is to m is to consider difference. All metrics between measures will be of the form. You take integral or with respect to mu, integral with respect to m, difference, and then take sup over f, which are Lipschitz with Lipschitz constant 1 or something like that. Meaning f of theta minus f of phi is bounded by constant times theta minus phi. So if that is a sort of, this is a Lipschitz distance between mu and m. Sometimes it is easier to, the distance with respect to continuous, so with respect to arcs, it tends to be worse than with respect to continuous functions or smooth functions. So this, you will certainly be able to bound this in terms of this. I think it should be easy. The other, but it could be better. Maybe you can do away with the log. I'm not too sure of that. No, I don't know. But this you can definitely bound in terms of this, I think. It should be easy. Yeah, it should be easy to do that. But I don't know the other way. But it's a good question. It may be considered. I'm not too sure. So yeah. So any other questions, comments?
Yeah, I had another question. So,
Yeah.
so are there families of polynomials, random polynomials, where you see like it's not uniform, but it's like supported on a ring type thing?
No, I mean, so with IID, no. The fact is, so this is a funny thing. So this was pretty much, so this erdastugan is from a very long time ago, and people have observed in 50s or sometime that this will easily give the for the random polynomial situation. That's when people ask questions about random polynomial. So provided, so what from these, what one gets here, I will just write this on the side and erase this maybe. So if we have a0, a1, an IID, let's say, and p of z is that a0 plus a and z to the n, then the roots, the angular distribution of roots converges to uniform. Okay, so this is one. This is true without IID as long as this is non-degenerate. So to say that the radial distribution converges to delta mass at 1. Okay, this happens if and only if expectation log plus. So let's say this is in probability, for example. Okay, so expectation log plus of this coefficients is finite. Okay, so if you take IID, yeah, I mean, so the angular distribution is always going to be uniform, but the radial distribution can be like this. So now your question was about the radial distribution, right? So if you violate this,
Right, I see.
people have this is a theorem due to Ibragimov and Saprosets.
I see.
Not so long ago, it is from 2011.
I see.
So even when this is, so this one, how do you get without the assumption, without any assumptions? That's the tricky part. So this one is okay. This is the question: how do if you don't have any assumptions of AIs, you cannot use Erdős-Turan. So how do you do that? It is in a very fine question because nobody cares about distributions which violate this. Maybe not, but still, it's a good answer. They found that it doesn't depend. Okay, they found a different trick. But when you violate this condition, so there is a study by Kabluchko and Zaprosets from 2014-15, sometime like that. Then different things happen. There are not one circle, but multiple circles. Some are vanishing.
Okay.
And they kind of distribute on these. So these are some, many of these may be vanishing or going to infinity, something like that. But there are some radii on which the most of the roots are distributed. But there are multiple radii on which that happens.
And the radii and the angle, they're like this is spherically symmetric, or?
Yeah. So in this case, the angles will be, because it's still IID, the angular distribution is always going to be uniform. On each of them, the angular distribution is uniform.
Right.
But there are multiple radii on which certain, and they analyze how much mass will fall on each of them and so on, that kind of stuff.
Right. Okay.
So there is a bunch of roots here, there is a bunch of roots here, there is a bunch of roots, but on these, each of those circles, it's uniformly distributed. Yeah. So that's what I know up to now. So maybe there are some other results also, but I'm not up to date.
I mean, if the coefficients grow exponentially fast in this for the random case, then at least some subsequence you will have measure concentrating near zero.
No, but here I'm taking IID. So if you take IID, that cannot happen, right? IID means, well, okay. So here when I'm saying IID with a fixed distribution. So as n changes, we're using the same distribution.
Yeah, but if expected log is infinite.
But even then, it's not that an will go exponentially. It's only like some lim sup.
Yeah, but that's enough for a subsequence, no? Or you can always find one subsequence for which the zeros are lying on arbitrary close circles near origin.
That's so you are saying some of these RIs are close to vanishing. Yeah,
All-
they are going
Yeah,
fast to zero. That is correct, actually. Yeah. So what Kaushik is saying is that, so just imagine that all the somehow what happens, it's a good intuitive point. If this is violated, what happens is occasionally AN tends to be extremely large. Okay, it's from Boyle-Cantelli. So imagine that you get to a stage where you for some n, AN tends to be very large and all these coefficients are kind of small or something like that. Then it is a bit like the polynomial z to the n. So all the roots will be very close to the, but with a very large coefficient. You can ignore the rest. When you take, sorry, not this. There should be a constant also. Yeah, a naught, let's say plus a naught equal to 0. This will give you zeros distributed on a circle very close to 0. So it will look like that. That's the point. Okay, any other questions, comments? Okay, if not, let me just indicate this. So I have a few minutes. I can easily do this. So how do I do this kind of stuff? So actually, this calculation I did is very helpful. I hadn't realized earlier. So as a part of this, just let's recall that I showed this, right? So I got this. From here, we get another thing. Okay, so remember that if I fix r less than 1, then 0 to 2 pi log mod e to the I theta minus r e to the I alpha. We are doing d theta over 2 pi. So here I did it with e to the I k theta, which is with k not equal to 0. Okay. But suppose I want to take the k equal to 0 term. You see, there is no k equal to 0 term. The 0 Fourier coefficient of this is 0. If you look at this function as a function of e to the I theta for fixed r less than 1 and fixed alpha, then there is no constant term, which means this integral is actually 0. So you fix any r less than 1 and e to the I alpha on the unit circle, this is 0. You agree? So this is what is helpful to me. So let me copy that result here. From that, everything will come. So for fixed r, so proof of, so for proof, let's do this. So recall that integral 0 to 2 pi log of e to the I theta minus r e to the I alpha d theta over 2 pi is 0 if r less than 1 and e to the I alpha is any point on the unit circle. Okay, so this is true. So what does that give me? So as a corollary, I will tell this. So if I look at integral 0 to 2 pi log of, let's write it in a slightly different way. R e to the I theta minus e to the I alpha d theta over 2 pi. What happens if r is less than, if r is bigger than 1? If r is bigger than 1, what I can do is, I'll just say here, if r is bigger than 1, let's pull out a log r out. Okay, let's write it as log r plus log e to the I theta minus 1 over r e to the I alpha. Right now 1 over r is less than 1, right? So because r is bigger than 1. So when 1 over r is less than 1, this will give me, this integral will give me 0. So what I am left with is log r average on the unit circle, which is log r, if r is bigger than 1. Now, if r is less than equal to 1, what do I get? I claim that I get just 0. Well, why is that? Yeah, so why is that? Well, because we can also write this as when r is less than equal to 1, we can just do one thing. We can pull out e to the I theta and e to the I alpha. So let's pull out log mod e to the I theta, which is 0, plus log mod e to the I alpha, plus log of 1 by r e to the minus I alpha minus e to the minus I theta, right? See, I'm writing the integrand. In the first case, I wrote the integrand like this. In the second case, I write the integrand like this, which is okay, right? I pull out e to the I theta, e to the I alpha. And what I'm left with is r e to the minus I alpha minus e to the minus I theta. Now these are 0. These are 0. And this is, well, there's a minus, but it is exactly an integral of the previous kind where r is less than 1. So this is actually going to give me 0. Right? It's exactly this integral where alpha is replaced by minus alpha and theta you're doing minus theta. So you're going around in the other direction, but it makes no difference. So it will be 0. So this you have. So this is the key point. Any questions? This is the whole point actually. This is the key integral after which we will get the whole thing. Any questions on this? Okay. So if not, now we'll take. So now if that is okay, then now we are in place. So write P of Z to be a n times Z minus R1 e to the I theta 1 dot 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 Z, sorry, there is no Zn, it is. So Z minus Rn e to the I theta. So this is what we have. And then what is h of p? Let's look at h of p is integral 0 to 2 pi log mod p of e to the I theta over an. Sorry, an a0, right? An a0 d theta over 2 pi, right? Log plus. Now what is that? Well, here when we do this, though, this will give me actually 1 second. If I do it like this, then this is h of p. That's correct. I don't want the log plus. I want with the log. Then it is easier. Maybe we'll come to the log plus later. Okay, so let's not do this. So just let's add this identity. Okay, over all theta j. Put alpha equal to. Okay, why did I write like this? Actually, this was the better form for me, I think. Yeah, what did I do? I don't know. I want to integrate over the unit circle and I want a minus. Okay, so sorry, I may not want this form. This is absolutely correct. But here what happens if r is bigger than 1? This is the key thing. So what is this when r is bigger than 1?
Yeah, log plus yeah, log r, yeah.
Is log r, right? Log r. So overall you can write this as log plus r. Okay, so that's all this. Okay, log. Sorry, I mean this intermediate thing I will erase. It's actually correct, but I wanted it in the original form. It looks like. Let me hold on to it till I finish. So I have this. So p of z. So put alpha equal to theta j and r equal to rj in the integral. So let's call this hash. In that, to get log mod e to the I theta minus rj e to the I theta j d theta over 2 pi 0 to 2 pi is going to give me log plus rj, right? Which is log rj if rj is bigger than 1, 0 otherwise. But what is this actually? So and then I sum it over j. Now what is this? So let's take this one. It is the integral 0 to 2 pi log of, when I take sum of the logs, it is log of the product. The product is e to the I theta minus zeta j. This is zeta j, right? This is everything except this. So it is log mod p of e to the I theta over an. See, mod p of e to the I theta over n is exactly the product of e to the I theta minus r1 e to the I theta 1 up to e to the I theta minus rn e to the I theta n, and the log will make it a sum. So I have this. It's kind of what I seem to want, but yeah, so I have this. Yeah, so I get this. Okay, so how do I relate it to log plus and log minus? Yeah, this is log plus rj. This is the Jensen's formula actually. This is actually Jensen's formula, but yeah, now what do I do? Right, okay, so let's do the same. For let's just write here 0 to 5. So I just okay, actually, what did I do? No. Well, half log a naught by a n. So this is what we get. I mean, I just pulled out. I wrote it in the form I want. P over square root a naught a n, and then I have. Sorry, I mean there may be a simpler way to say all this, but it's well, one can get to there in many ways. Hopefully, I will also get there. So this one, the first one, let's write it like this: log of mod p of e to the I theta over square root a naught a n d theta over 2 pi. But you know what is the a naught over a n? A naught over a n is the product of the roots, plus minus. Therefore, log mod that is actually half of log rj plus 1 to n. So you transfer it to the other side. So log plus rj, this is only, so this is actually sum of log rj over j such that rj is bigger than 1 is equal to half of this whole sum plus this. So if you transfer it to the other side, you get log rj over rj bigger than 1 minus log rj over rj less than 1 is going to give you, there is a 1/2, so that I put on this side, I get 2 times 0 to 2 pi log mod p of e to the I theta over a naught a n d theta over 2 pi. Okay, so that's pretty much it. So what I have here is, it is basically the sum over j of log of either rj max 1 over rj. Right? I mean, so if rj is bigger than 1, then this is log rj. If rj is less than 1, it is minus log rj. So this is actually what this is. And this you can bound by the positive part. The negative part is negative, of course. So which is 2 times h of p. So this is what I had in the first instance. So the first claim is that if I sum log of rj max 1 over rj, then I get max 2 h of p. Okay, since I mentioned it, so let me just say on the side. So Jensen's formula is a very useful one. If you haven't seen it, I mean, in complex analysis class, sometimes it is done. Jensen's formula is a very useful one. It says that if f is analytic in a neighborhood of, let's say, the disk of radius 0 with r, with some neighborhood of that, in a neighborhood of that, then if you take integral of logarithm minus log mod f of 0, assuming that f of 0 is not 0, otherwise you can modify it, that will give me the sum over all roots zetas are such that f zeta is 0 with mod zeta less than r. Okay, so it gives you in complex analysis, Cauchy's theorem and many argument principle. All these are ways in which you can get information about roots from integrals on the boundary. So this is yet another one of that kind, extremely useful. So it tells you that you can get information about roots inside from the integral on the boundary. Okay, so this is Jensen's formula. So basically, I derived it for polynomials here. From polynomial to go to analytic functions is not a big deal. One can do it fairly easily. But so one can get from here to Jensen's formula also. If you can always look at Rudin's real and complex analysis, many other places. Now, in the last couple of minutes, let me say how this comes from this by just Chebyshev inequality like thing. Okay, so because we have, so this proves one. For two, so for each root which is for each root which is below R or above 1 by R, okay, if Rj is less than R or Rj is bigger than 1 by R, then log of Rj max 1 over Rj is greater than equal to log 1 over R, right? So fix R less than 1. So if you have R less than 1, R is here, 1 is here, 1 by R is somewhere here. So if you are either here or here, in absolute value, the log is going to be bigger than log 1 over R. Therefore, and all these are positive numbers, by the way. These are positive numbers. These are positive numbers. Hence, the number of such things.
It's 1 o'clock.
Each of them gives a contribution of at least log 1 over R. So that total and the rest of them are non-negative. All terms are non-negative. Okay, here. So you drop all the terms, all the RJs which are between 1 R and 1 by R, you drop. These ones will give me this is less than equal to 2h of P. And that is it. So this is nothing but the new P of 0 R union 1 by R to infinity times n. Because new P and then there is an extra log 1 over R. So new P of this is bounded by 2h of P over n times log 1 over R, which is what I had done here. Okay, so that is all there is. So that's it. I'll end here. Any questions, comments, etc.?
So regarding Shaumendu's earlier question, whether you can find this limiting zeros on rings kind of thing, if instead of taking polynomials, if you allow both plus z power k and z power minus k, both Laurent polynomials, then you can get.
Well,
so instead of taking polynomials, you take Pm of z plus Qn of z, where n is Qn is like 1 by z plus whatever, a1 by z, a2 by z squared, and so on. In that way, if you take Laurent polynomials, then one can get their zero distribution in rings.
But you are taking coefficients of different distributions for the two parts. No, if you can take the same, then you can pull out a 1 by z to the n and it's a polynomial, right?
Yeah, but you can take different, you can match it with AK, well, I mean xi k AK and BK xi k, right?
Okay, I didn't understand what that was. What I meant was if you have a power series, I mean, so you have some a minus n over z to the n plus dot 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 plus
yeah,
a
but
naught.
I mean that there is a minus n and then a deterministic part, that is a minus n times say c minus n, where c is c
If you
minus
change
n.
the coefficient, then they are not IID.
Yeah.
Okay. Yeah, by the way, if you change the coefficients, if they are not IID, you don't even need this. I mean, you can get, for example, okay, so even with polynomials, I think fine. So even with polynomials, if you take very famously known as okay, these are also studied. If you take polynomials like this,
I see.
or polynomials like this,
Or like a random metric, a characteristic polynomial of random matrices would also give you.
yeah, but there we don't have, okay, they are random polynomials, but when we say random polynomials, we usually mean we are putting distribution on coefficients. Usually characteristic polynomial, we absolutely don't understand how the coefficients look. They are
Yeah.
highly dependent and all that.
Yeah.
So, but these ones are very interesting polynomials. So you take a case to be IID, but you have put these coefficients. You can think of putting any other thing, but these ones are special. In this case, the roots are uniformly distributed, meaning you will find them everywhere in a disk of radius square root n. It's like if you know in random matrix the Ginebra ensemble, it is very much like that. This one. This one, it is actually if you stereographically project the complex plane to the sphere, then it is uniformly distributed there. So on complex plane, it is some kind of a Cauchy distribution, but yeah. So if you stereographic, so there are, yeah, if you don't make it IID, then you can get all sorts of behavior. Yes. You can get, so this is what Kaushik was saying there also, you can put some constants, then you can get other behavior.
No, because he had asked for specifically distribution on rings. Then this one, that annuli, this whatever Laurent polynomials will give you distribution on rings.
Right. So if you can make, yes, so right. So yeah, what I mean is you can get all sorts of things also. I mean, you can get pretty much any sort of, not any sort, but a lot of things like this. Yeah, for annuli you can do this, but with some coefficients here.
So Manju, what are you planning to do next time?
Yeah, so I was thinking of going to expander graphs construction.
Okay. And when will the course get over?
It is shortly. I mean, November 26th is the last day of classes. So I have only like 3 classes, maybe 2 classes this time, and maybe 2 next week or something like that.
Okay. Okay.
Yeah, next week it will get over.
Okay. Yeah. Thanks, Manju.
Okay.